Welcome back. Last time we talked about evidence of the age of the Earth from sedimentary rocks and fossils. This time let's talk a little bit about other types of rocks and also some other evidence from Earth sciences. Let's begin with igneous rock. Igneous rock is rock which is formed by molten magma, hot molten rock, cooling either underground, in which case we call it intrusive rock, or above ground, in which case we call it volcanic rock. Now, what happens when this hot rock cools is that crystals are formed. And if crystals are large, that means that the rock cooled over a long period of time. It cooled slowly. So volcanic rock, rock that is lava spilling out on the surface of the Earth, tends to cool very quickly. The crystals within it are very, very fine. But rock that is cooling deep within the Earth develops long crystals, large crystals. And granite, for example, is a good example of this type of rock. If you look at the kinds of rocks that you see in a place like the Sierra Nevada, for example, Yosemite National Park in the United States, these huge outcrops of rocks, or these huge monoliths, are mostly granite. They are igneous rock, rock that apparently was formed deep underground. What happens is this: magma is forced up from deep within the Earth. It pushes up into overlying layers of rock, in many cases sedimentary rock. It forces its way up in great plumes called plutons, and then it cools underground, sometimes many miles underground. The sheer quantity of rock and the depth at which it's buried and the composition of the rock determine how long it takes for this to cool. But when geologists look at what's known as the batholith of the Sierra Nevada, this huge amount of granite that makes up the Sierra Nevada mountains, and they try to estimate the time it would have taken for this to cool underground, they come up with estimates that begin in the hundreds of thousands of years and end somewhere in the millions of years. It's impossible to know for certain, because it's impossible to know for certain just how deeply these were buried and just how much was formed at one particular time. But it seems that it takes a very long time for this rock to cool when it's under the conditions of being deep in the Earth. And laboratory experiments confirm this. So what you have in the case of mountains like the Sierra Nevada is this kind of a scenario. First of all, there is a deposition of sedimentary rock, or perhaps there's volcanic rock. And then deep within the Earth, underneath all of this rock, there is an upsurge of magma. The great pluton of magma is formed underneath all of this, or within all of this. That cools, taking a very long time to cool, and then the entire thing is lifted through the tectonic process that built the Sierra Nevada. That is a process of collision of plates that buckles the Earth and pushes all of this up. And then the overlying strata of rock that were there in the first place are largely eroded away. In the Sierra Nevada, geologists find remnants of what they believe is the sedimentary rock that used to cover the entire batholith. Again, we're looking here at very, very slow processes. The deposition, first of all, of sedimentary rock, then the formation and cooling of rock deep underground, then the lifting of this rock, and then the erosion of the overlying rock. This is not something geologists believe can take place in a few thousand years. It requires much more time than that. What about metamorphic rock? Metamorphic rock is rock. It's either sedimentary rock or igneous rock or even other metamorphic rock that has been changed in its character, in its structure by heat and pressure. Metamorphic rock can, I think, in some cases be created very quickly. If you go to a meteor crater in Arizona and you look at the rocks in that area, I believe that there are igneous rocks that were formed when the asteroid that dug out that crater hit. Probably they were formed instantaneously. They were sedimentary rocks that, under the tremendous pressure of this tremendous impact, simply were malformed or deformed by the pressure. For the most part, though, metamorphic rocks are formed deep underground because in order for the structure of the rock to be changed, as geologists can tell that it has been changed, there has to be a combination of very great pressure and very great heat. Sometimes I think this takes place not too deep at fault zones where there's tremendous pressure on rocks and they're being squeezed. But it's possible for geologists to distinguish those metamorphic rocks from those that are formed simply deep in the earth because of the nature of the crystal formation that occurs during the metamorphosis. Rocks that have been formed deep in the earth are found on the earth's surface. In some cases, laboratory experiments on these sorts of rocks have shown that these rocks had to have been buried to a depth of as much as 7 miles in order to have been deformed in the way that they are deformed. So again, we're thinking about a multi-stage process. You have the deposition of sedimentary rocks, perhaps some volcanic rocks. You have this going on until there are rocks 7 miles down. In some cases, originally sedimentary rocks. These rocks, under the tremendous pressure and at the great heat at that depth, are distorted, they are changed, they are metamorphosed, so to speak. And then there is a process by which these are lifted up to the surface of the earth. Again, these are tectonic processes that make mountains and so forth, and the overlying rocks are eroded away, and then you find these rocks on the surface of the earth. Geologists just don't have a good explanation for this. That does not involve this kind of multi-step process, and that does not involve tremendous amounts of time. This is not something that can occur in just a few thousand years. It occurs over very, very long stretches of time. How old are the rocks of the earth? Up until the early 20th century, nobody really had any good way of figuring this out. It was at the very end of the 19th century that radioactivity was discovered. Very early in the 20th century, people began to realize that you could use radioactivity to date things. The processes of radiometric dating are complicated, very complicated in detail, but the basic concept is simple, and I suspect that you're already very familiar with this. Many, many elements in the periodic table have radioactive isotopes, that is, forms of these elements that decay radioactively. Each isotope has its own decay rate. This is described or referred to as the half-life. This is the length of time it takes for half of the original radioactive isotope to decay into its daughter isotope. And these vary from element to element. And these rates have been found to be very, very consistent. A lot of work was done early in the 20th century to see if you could change rates of radioactive decay. If you put rocks or materials under very high pressure, if you made them very cold, if you made them very hot, if you did various other things to change them or to affect them, could you change rates of radiometric decay? And the only changes that occurred were very, very tiny, very, very small. Radioactive decay appears to be something that's very, very steady, very dependable, and the half-lives of many, many isotopes have been determined by laboratory experiments, and so they are well known to scientists. It's possible then to go to the field to find rocks and to date rocks using this method. That is, to measure how much of the original radioactive isotope is still there and how much of the daughter isotope is there, and from this ratio to be able to figure out the age of the earth. In many cases, it's possible to use multiple methods to do this. That is, in many cases, because the rocks are very old, there are many methods of radiometric dating that overlap. Many different isotopes have very, very long half-lives. It's possible to use multiple isotopes to date the same rock. And when this is done, you come up with very, very similar values, which gives scientists a great deal of confidence that this works. It's very difficult to use radiometric dating to date sedimentary rocks, because sedimentary rocks, by their nature, are formed from sediment, that is, from grains of rock that are the result of older rocks that have eroded. And so what you wind up doing if you simply try to do radiometric dating of sedimentary rocks is you wind up dating the original rocks, the parent rocks, rather than the sedimentary rocks themselves. But there are ways around this. In many places in the world, there are volcanic intrusions or igneous intrusions into the sedimentary layers. These can be dated because igneous rock is melted, and when it hardens, that's when the radiometric clock starts ticking. In other cases, there is volcanic ash. A volcano has occurred, ash has fallen on the ground, it has become incorporated into the sedimentary layers, into the strata, and you can date the crystals within the volcanic ash. And when this is done, what is found is, as you would expect, that deeper layers of ash or deeper layers of volcanic rock are found to be older than those that are higher. It fits precisely with what scientists believe to be the nature of the geologic column. Well, just how old is the Earth? The oldest rocks that have been found on Earth, I believe, are somewhat shy of 4 billion years. There are crystals, zircon crystals, that have been found in Australia that are dated to about 4.4 billion years. Did I say 4 billion years or 4 million years? I should have said 4 billion years for Earth rocks. Zircon crystals to about 4.4 billion. Moon rocks and meteorites have been dated to a little bit beyond that, 4.5 up to maybe 4.6 billion years old. And because it's possible to use multiple methods to date these rocks, and if you want to see charts of this, go to Dalrymple's book, Ancient Earth, Ancient Skies. He shows you precisely how specific rocks, moon rocks and meteorites, have been dated using a variety of different methods. You wind up in the end with an estimate of the age of the solar system of somewhere around 4.55 or 4.56 billion years old. I don't know exactly what the scientists are saying now, but it's in that vicinity, simply from the radiometric dates. Now, before we leave geology, let's just talk about a couple of other things from the earth sciences. There appear to be methods that God has given to us to collect data from the past. One of these is ice layers. In Iceland, or in Greenland rather, it's possible to drill down through the ice and drill down through what appear to be 100,000 years worth of ice layers. In Antarctica, it's possible to drill down through 800,000 years of ice layers. It's also possible to use lake sediments in a place like Lake Baikal in Siberia, drill down through those sediments and gain information about Earth's climate and other things happening in the past from these sediments. Lake Baikal has a record that goes back about 250,000 years, scientists believe. And it's not simply that there are layers that can easily be explained away as something that might have happened all in one year. Instead, what you find as you look into these layers is information that seems to tell a history of the Earth over this period of time. In the case of Antarctic ice, 800,000 years. For example, in the air that's trapped in the ice, you can analyze this air, you can find rising or decreasing levels of carbon dioxide or other elements in the air. You can actually chart these and see the changes in the Earth's atmosphere, changes in Earth's temperature over long periods of time. These appear to be records of events, not simply layers that could easily be interpreted in some other way. So we have from the sedimentary rocks, from the igneous rocks, from the metamorphic rocks, and then from these various data gathering mechanisms. And I've only mentioned two, but there are others. Corals also gather information and preserve information about Earth's past. From these various means of looking at the Earth's past, geologists are persuaded that the evidence is overwhelming that the Earth is old. And with radiometric dating, they believe they can actually date the Earth to about 4.5 billion years. They are not saying this simply because they're trying to provide cover for evolutionists. And not all of them are evolutionists. They're saying it because they really believe this is where the evidence points us. They think that the evidence is incontrovertible. Well, we'll come back. We'll talk next time about astronomy. Thanks very much for watching.